Alright, hello everybody, and today we're going to be evaluating the improper integral from 0 to infinity of 2 times x squared plus 1 times e to the minus x squared. So this is a question from the MIT Integration Bee back in 2006, I'm quite sure. And this is quite a nice integral to evaluate because we have this e to the minus x squared right here, which is pretty much the Gaussian integral. So to evaluate this integral, we will need to know the Gaussian integral, which is the integral from negative infinity to infinity of e to the minus x squared times dx, and we should all know that it evaluates to the square root of pi. I'm not going to derive this in this video, but this is a nice integral identity we should know. So the nice thing is with this function is that it's symmetric across the y-axis. So that means if we split the interval of integration up into 2, well then it divides the area by 2. So becomes square root of pi over 2, and that nicely matches with our interval right here for this question. So how can we approach this question right here? Well, the first thing I did was I expanded out this bracket right here. So this becomes the integral from 0 to infinity of 2 times x squared e to the minus x squared, and I'm going to split the integral up into 2 as well. So we're going to have plus another integral from 0 to infinity. 1 times this thing is e to the minus x squared times dx. And the nice thing is this part right here is the exact same thing as this integral, which is square root of pi over 2. So now this thing right here is the square root of pi over 2. And now all we're really left with is this integral right here. So notice we have an x squared and an x squared right here. That just kind of calls for a substitution. So we're going to let a new variable, let's say u, be equal to x squared, which means that du is equal to 2x times dx. And using this substitution right here, we can kind of say that x is the square root of u, and we can do the replacement right here. So this is 2 times the square root of u times dx, and rearranging things around, we're going to have dx being equal to 1 over 2 square root of u times du. Okay, now we can substitute everything back in. And notice our bounds won't change as well because plugging 0 into here, so we're going to get 0 for u. Plugging infinity into here, we're still going to get infinity. So we're still going to have the exact same bounds. And then now we're going to have 2. X squared becomes a u. Then we're going to have e to the minus. And then x squared right here again becomes a u. Then dx becomes 1 over 2 times the square root of u times du. Okay, and now the nice thing is that these 2's will cancel out, and we can do some cancellations with these square roots right here. So now we have the integral from 0 to infinity of the square root of u times e to the minus u. And now we have this integral right here, and this kind of looks like something we can use integration by parts on. So let's put that over here. I think we can fit that in a little bit. So now integration by parts, we're going to be using the di method. So di plus minus, and then now what do we want to differentiate? I'm going to differentiate the square root of u because integrating it would just be a complete mess. So differentiating that, we're going to get 1 over 2 times the square root of u. And then for our integration right here, we're going to be using e to the minus u, which will turn into minus e to the minus u. Okay, so the answer to this integral is just this product of the diagonal right here, and the product of this row at the bottom right here is still an integral itself. So this integral evaluates to the square root of u times e to the minus u with a negative, evaluated from 0 to infinity. And remember, this row right here at the bottom is still an integral, so we have a double negative, so that becomes a plus. Then we have an integral from 0 to infinity of 1 over 2 times the square root of u times e to the minus u du. Okay, so looking at this part right here, this is actually quite nice because taking the limit of that as our u approaches infinity right here, this exponential term will just go to 0, which just kills the whole thing. And similarly, plugging a 0 into here, this square root of u will just go to 0, and that's just going to kill everything. So overall, this whole entire thing is just a 0, so we don't need to worry about that anymore. All we really need to worry about is this integral right here. And you can actually do a nice little trick that I kind of came up with for this type of integral, because notice we have 1 over 2 times the square root of u. And if you know your calculus well, you'll know that this thing right here, this 1 over 2 times the square root of u, is exactly the derivative of the square root of u. So what we can do is do a kind of reverse substitution, because if we take this part times this part, so if we have 1 over 2 times the square root of u times du, we can say that it's equal to some change in a new variable, let's call it t. And if you integrate both sides right here, what you actually get is the square root of u, because the integral of 1 over 2 root u is root u, and integrating dt will just give you t. So that implies that u is equal to t squared. So pretty much with this thing right here, this kind of reverse substitution method right here, we can rewrite this integral a little bit, and notice the bounds will remain the same as well because of this substitution right here. So now this is equal to, we have our 0 right here, which we can disregard. So we have the integral from 0 to infinity of now 1 over 2 times the square root of u times du. That's just going to evaluate to dt in the end. And now we have e to the minus u, but remember u is t squared, so we have e to the minus t squared, which is really quite nice, because this thing right here will also evaluate to this half a Gaussian integral, which is the square root of pi over 2. So what exactly did we just find right here? We found that this first integral right here also evaluates to the square root of pi over 2. So let's clean things up a little bit right here. This whole thing right here is also the square root of pi over 2. So overall, our integral at the very start evaluates to the square root of pi over 2 plus the square root of pi over 2, which overall becomes just the square root of pi itself. So this thing right here is the answer to our original integral right here, which is quite nice. So I hope you guys enjoyed this quick little video, and I'll see everyone next time.